Greetings, my name is Jasmin Jahic and I would like to give you a short introduction into the roles that software architecture has in continuous software engineering. This is a short overview of a course that I'm teaching at the University of Cambridge. Let's discuss first how do we actually develop software applications. One way to develop software is to have an idea, to sit in front of your computer and to start implementing that idea. And many great applications have originated in this way. In order to develop software in this way, it is necessary that you have a good set of skills in terms of solving logical problems and that you have enough knowledge in terms of programming in a certain programming language. Besides this context, there exist other contexts for software development. And one of these is so-called digitalization. So in many business domains, which are traditionally not associated with software at all, there is a need to attract new customers. In order to attract new customers, it is necessary to provide new features of those systems. In order to provide new features, it's actually necessary to innovate. So these businesses see software as a tool that is going to help them to innovate within their specific business domain. Therefore, they go through the process of digitalization. That means turning their business into a digital one, offering digital services, and employing software engineers as contractors to provide them a software, a tool that is going to provide new features in their business domain. That means if we, of course, compare it with the first scenario that we have discussed, that means that there are suddenly many more people involved into a software project. Software engineers, marketing people, investors, and so on and so on. All of these people that are somehow interested in the outcome of the project or affected by the outcome of the project are called stakeholders. And these stakeholders have their specific wishes in the context of the project, and they have specific concerns. So their wishes and their concerns are called requirements in the context of the software engineering. So how the software engineering development process works in this case, in this second context? Well, software engineering team takes these requirements and they start software development. They organize their software development using development methodologies and infrastructure. That means that they use good engineering practices in order to work on the work assignment, in order to create tests, to enable automatic testing of their software, to enable the integration of the work that different developers and engineers do, to enable the deployment of the product or part of the product that they develop, and sometimes even to create some documentation. You might be familiar with some of these development methodologies and some of these infrastructure such as Agile, Scrum, continuous engineering idea, and so on and so on. So what we're actually talking about here is software engineering. That means that besides programming skills and the skills for solving logical problems, there is a certain engineering practice, certain set of engineering practices for development of the software and for the whole process and the whole infrastructure for software engineering. Now, if we take a look at this development cycle from the outside, everything seems to be perfect and wonderful. That is until a team does not produce certain parts of software, so the first results, the first artifacts of the software engineering process. And then problems begin. Some stakeholders might complain that some of their requirements were completely ignored. Some other stakeholders might complain that the development team was actually late. For other stakeholders, it could be very difficult to understand what did development team actually produce. If the software is not intuitive enough or if the software does not have appropriate documentation, some users might complain that they are not really sure how to use that software. Other users might complain that some of the quality properties of the software are pretty bad. So that means the software is doing what software is supposed to do, but for example, it is too slow. On the other hand, development team, engineering team might say, okay, but our software is doing as it should work. It is doing what it's supposed to do. It's working as it should work. Sometimes they might even go so far away to say, okay, to say to other stakeholders, you don't really know what you want. Of course, that's not the problem. That's not the solution to the problem. So what exactly are the challenges in this case? Well, the challenges in this case is that the prioritization of the requirements was not done properly. That there was not enough focus on the quality properties of the software. And here we're talking about two sets of the possible quality properties. The first set concerns with the quality properties that end user is going to perceive from software product. That means how fast the software is, whether it's secure or not, or if it's some more complex software system, whether that software system is safe. Other part of the quality properties is actually related to the quality of developed software itself and its design. That means whether it's possible to extend this software system in an easy way, is it hard to maintain this software and source code, and so on and so on. Finally, it could be that some of the challenges are really on the design level. That means that the design of the software system was not made in a proper way, because if it's not made in a proper way, it did not enable developers to properly work in parallel. That means that they also had issues with integrating their work which they developed in parallel. So what is the solution to these problems? Well, software architecture is trying to solve these issues, and there exist many definitions about what the software architecture really is. Here are some of them, and I have highlighted some of the important wording of these definitions. So for example, in the first one, it says that the software architecture actually represents principles that are guiding design and evolution of the software system. In the second definition, it said that the software architecture is a set of design decisions about a software system. And the third one, which is my favorite and the closest to the software engineering and software development, says the software architecture of a program or computing system is the structure or structures of the system which comprise software elements, the externally visible properties of those elements, and the relationships among them. If we put this into a context of software development and software engineering, we get something like this. So it is necessary to have software system architecture in order to enable management on the project and on the system level, and in order to enable actually proper system engineering. Besides this, software system architecture acts as a communication medium between the business side and the technology side. That means that the software architecture is a way to enable the communication between the different stakeholders. So let's go back to the set of the challenges that we discussed at the beginning. When we talk about prioritization, it's necessary to actually capture the important requirements that different stakeholders have about the system. It's necessary to properly summarize them, and it's necessary to understand what are their priorities. From these, it's necessary to identify those requirements that have high priority, which means that they are actually the requirements which are driving the project. Usually, stakeholders have implicit understanding about their quality properties of a software system. That means they usually assume that the system is going to be fast enough, that it's going to be secure enough, and they, in the best case, they usually say, okay, it's necessary for our system to be safe and secure, which in terms of the quantification doesn't mean anything. Therefore, quality itself is a big important driver of software systems. For these drivers, it's necessary to make proper design decisions. That means it's necessary to design a system, to create a design of a system that is going to properly meet these drivers, and besides that, enable also the division of the work among developers. So that means that they can work independently and in the end be able to integrate their work. Now, we have seen that one of the big problems that exist in software architecture is actually communication between different stakeholders. Why is this happening? Well, it could be that we have different stakeholders which have a very different background in terms of education, in terms of their goals, in terms of their views of the system. Therefore, for each stakeholder, it is necessary to provide a proper view and a proper perspective of a system. Now, let's investigate each one of these into details. When we talk about requirements and when we talk about the drivers, we want to capture a set of requirements which are actually driving a project. And these are architecturally significant requirements. We divide them usually in 4 groups. What is important for business, so what is really significant from the business point of view, what are the most significant functionalities of a software system, what are important quality properties of a software system, and are there any constraints? For example, it's necessary to use open source software, or it's necessary to use Linux, or this application is going to be deployed both on iOS and Android. So these type of the constraints. So these actually become the drivers, the main drivers of a software system. Now, for these drivers, it's necessary to make proper design decisions. When architects are making design decisions about their software, in order to meet their drivers, they need to discuss several things. The first one is what is really the rationale for making this decision. So why are we making this decision and what this decision is going to achieve. Now, if there is a certain decision of a software system, for example, to have 2 or 5 or 10 components which are communicating in a certain way, what is the advantage of this design? What are the disadvantages of this design? Because probably there are some disadvantages in some different other quality properties of a software system. What are the trade-offs? If a certain decision is increasing or making better some quality property of a system, it could be that it has compromised other quality property of a system. When it comes to design decisions, usually design space is huge and it is really hard to make proper design decisions. Making design decisions is a very long and a very expensive process. That's why a good practice is to collect all the discussed decisions, choose the ones that seems the most adequate, considering their advantages, disadvantages, trade-off, but also to document all those alternatives which were discussed but were rejected. The reason why we do this, in order not to go through the whole process again. And of course to save some time. So that means if after some time somebody has a brand new idea, it's just necessary to go through the documentation and see why this decision was discarded. Okay, so finally we are reaching at the perspective and the communication. And perspective in the communication is important because of one aspect. It could be that 2 or more stakeholders are looking at the same system and they're seeing something completely different. So in this case, on this slide, we see 2 representations of the same object. Technically, in both cases, this is a building. On the left side, we see a building from outside, and on the right side, we see actually some pipes which are probably important for plumbers who need to maintain them and fix them. The point here is whenever we are representing or presenting software system to different stakeholders, it is necessary to understand what kind of terminology these stakeholders understand and what are the properties of a software system in which stakeholders have interest. It doesn't make sense to present to business stakeholders something about efficiency of algorithms and the set of the classes that are used to implement the software system. Also, it doesn't make always much sense to present to developers the marketing strategies, and in which case different components in a system are going to enable these marketing strategies. So for different stakeholders, it's necessary to choose appropriate terminology and appropriate representation. So when we discuss software architecture, what we actually are discussing are the concepts and the principles that are helping us to solve these challenges. In this context, in the context of the course that I'm teaching, we discuss how to actually recognize which requirements are significant for software system and how to capture them using different templates. The next thing that we usually discuss is how to manage the complexity of a software system. That means how to recognize some designs which are considered as anti-patterns, how to recognize them and how to eliminate them, and how to focus on a set of good patterns which are guaranteeing certain good quality of a software and some tactics which are enabling good quality properties of a software. Now, in context of this complexity management, ensuring the quality, it's necessary to make proper decisions. I have said just a few slides ago that making decisions in a software system is really hard. One of the reasons for this is that the design space is so huge. It's possible to make a huge number of very different design decisions. How can we know that these decisions are adequate in order to meet the quality requirements, the functional requirements, so basically important requirements, the drivers that exist in our system? This is really hard, and we usually discuss what are different approaches for comparing different decisions. Once decisions have been made, are there any approaches and concepts that help us to evaluate whether these design decisions are adequate for our set of the requirements? Finally, it's necessary to enable the communication between different stakeholders, and in order to do this, we discuss what are different so-called viewpoints that help us with representing different properties of a software system to different stakeholders. Now, we discussed all of this in the context of several application domains. For example, Industry 4.0, autonomous systems, agriculture, and so on. So what is software architecture effectively doing? It is establishing a structure in terms of software engineering. It is making important architectural decisions. If architects do not make architectural decisions, someone is going to make them. Now, our hope is that with the software architecture, architects are the ones who are making important architectural decisions, not developers. So therefore, establishing a structure. And establishing a structure in terms of stakeholders, that means establishing a structure on different enterprises that are participating in a software engineering project. Of course, this is not the whole full story of the challenges and the concepts that are covered in this course and that the software architecture is tackling. Some of the other challenges which exist are how to reuse a source code. Besides the source code, which can be reused in certain contexts, it's also very valuable if it's possible to reuse architectural knowledge, because architects and developers spend a lot of time discussing what is the best way to design and implement their software. So if there are certain sets of design decisions gathered into some patterns of design, how to actually reuse this. Once there is an architecture, and after some time that some parts of this architecture are implemented, the question is how to evaluate this architecture. If this architecture is still fulfilling all those requirements that different stakeholders have from it. A more advanced topic is how to actually organize product lines of software systems. So to produce really different product lines of a software system with variation in parameters. After all of these things are covered, there are two very important practical parts of software architecture. The first one is how to integrate software architecture process with the continuous engineering process, because software architecture is not just a phase. Software architecture is an action that happens in parallel with software engineering, with software development. And something that is a big research challenge and that is following us as a big challenge in software engineering and software architecture is how to actually perform reverse engineering. That means how to prove that what has been discussed and agreed on the design level is actually really implemented in the software system. To this day, there are certain advances in this area, but it remains an unresolved problem. So that would be everything. That would be a short overview of the course. I hope I gave you the idea what software architecture as a discipline is actually covering. Thank you for your attention, and if you have any questions, feel free to contact me via email.